discussing the so-called critical section problem. Each process has a segment of code called a critical section, in which the process may be changing common variables, updating a table, writing a file, and so on. So, such as this example just now we look at. In consumer process, this is critical section because this statement assigns the shared variable counter. And in producer process, this is critical section because it assigns the shared variable counter. So this is critical section, okay? And the important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. So that means if the consumer process assigns the counter, then the system should now allow the producer assigns the same sharing variable. Okay. That is, no two processes are executing in their critical section at the same time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. Like this, is the entry section. And the critical section may be followed by an exit section. The remaining code is the remainder section. So we can say this is the general the general structure of a typical process. We have entry section, then critical section, and exit section, and then remainder section. Considering the critical section problem, actually, we doesn't care remainder section. We only care how to code entry section and how to code exit section to ensure at any time no two processes enter their critical section. Okay. So this is critical section problem. A solution to the critical section problem must satisfy the following three requirements. First, mutual exclusion. We already talked about it till now, okay? If process PR is executing in its critical section, then no other processes can be executing in their critical sections. 2. Progress. If no process is executing in its critical section, and there exist some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Third, bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. We assume that each process is executing at a non-zero speed. However, we can make no assumption concerning the relative speed of the n processes. At a given point in time, many kernel mode processes may be active in the operating system. As a result, the code implementing an operating system kernel code is subject to several possible risk conditions. Consider as an example a kernel data structure that maintains a list of all open files in the system. This list must be modified when a new file is opened or closed. If two processes were to open files simultaneously, the separate updates to this list could result in a race condition. Other kernel structures that are prone to possible race conditions include structures for maintaining memory allocation, for maintaining process lists, and for interrupt handling. It is up to kernel developers to ensure that the operating system is free from such risk conditions. Two general approaches are used to handle critical sections in operating system: preemptive kernels and non-preemptive kernels. A preemptive kernel allows a process to be preempted while it is running in kernel mode. A non-preemptive kernel does not allow a process running in kernel mode to be preempted. A kernel mode process will run until it exits kernel mode blocks or voluntarily use control of the CPU. So it is free from risk conditions because only one kernel process is active in the kernel at a time. But obviously, a non-preemptive kernel is essentially free from risk conditions. But for preemptive kernels, the programmers must carefully design to ensure that shared kernel data are free from risk conditions. Preemptive kernels are especially difficult to design for symmetric multiple processor architectures, since in these environments it is possible for two kernel mode processes to run simultaneously on different processors. One then would anyone favor a preemptive kernel over a non-preemptive kernel one. A preemptive kernel may be more responsive since there is less risk that a kernel mode process will run for an arbitrarily long period before relinquishing the processor to waiting processes. Furthermore, a preemptive kernel is more suitable for real-time programmer, as it will allow a real-time process to preempt a process currently running in the kernel.